So let's take a step back now and just look at some slightly less dire outcomes from type 1 and type 2 errors. So a test is made of the null hypothesis sigma equals 0.5 ppm parts per million versus sigma is greater than zero point 0.5 parts per million. Now the true value of sigma is 0.6. Now think about what that means. If the true value is actually 0.6, then in reality H1 is actually true. And H0 was rejected. So now, did we make a correct decision, or do we make a type 1 error or a type 2 error? So let's think about this. The true value is zero point 0.6. So let's go back to this table over here. If the true value is actually 0.6, that means that H0 is actually true. So you're on the right-hand side of this column over here. So now you have to think, all right, I'm in the right column. So did I make a decision to not reject the null? Because if I didn't reject the null, that's a type 1 error. But if I rejected the null, that's a correct decision. So let me scroll back. We rejected the null, so that means that we made a correct decision on this one. Now, a test is made of mu equals 454 grams versus mu is not equal to 454 grams. And the true value is actually 454. So think about what that's saying. That's saying that the null is actually true, but I rejected it. All right, so looking back at the table, if the null is actually true, it really is 454, that means I'm in the left column over here. If I reject the null hypothesis, then that's a type 1 error. I should not have rejected it, and I did. So this would be a type 1 error. And in case you're missing it, that table on the previous page should go right into the notes, right? Because you don't have to memorize this, you have to be able to apply it. All right, now one last test. The null hypothesis is that P is equal to 20%. The alternative is that P is less than 20%. The true value of P is actually 0.17. Okay, well, if it's really truly 0.17, that means that the alternative is actually what's true. It really is less than 20%. And I did not reject the 20%. Okay, so it really is less than. It really is the alternative. So let me scroll back. It truly is the alternative, but I did not reject the null. I made a type 2 error. So have this table right here put right onto your note sheet. Very important to know that for the exam and for the final exam. And here we are here with a type 2 error. All right, so now we have a sense of how to gauge correct decisions, type 1 and type 2 errors. This leads us into what I promised was the point of all of this, which is, well, there's several points, but one of the big points is that this is what alpha is. Alpha is called your level of significance. So when you see that symbol, it's the same as saying the level of significance, and that is the probability of a type 1 error, the probability of that false conviction, right? That I rejected the null, but I shouldn't have, right here, the type 1 error there. Which, of course, in the sake of criminal justice is very, very bad. That is going to be given to you. You're not going to have to generally figure it out. So researchers in the field, they'll actually determine what they want their probability of type 1 error to be, and they'll go from there. Now, beta was a symbol you haven't seen before. It looks like a B, but it has like an extra little tail on the end of it. It's kind of at an angle. That's beta, B-E-T-A, pronounced beta in Greek. And it's the probability of a type 2 error. So it's the probability of not rejecting the null hypothesis when the null hypothesis was false. Beta is actually much more difficult to calculate and work with, so we don't do a lot with it, but suffice it to say that it's there, and we'll work with it just a touch in terms of its relationship with alpha. Speaking of which, let's look at the relationship between alpha and beta. And I honestly think it's easier to kind of look at this with a context. So let me scroll back up here to the criminal defense example, sorry. So if you're really, really, really worried about the type 1 error, and why wouldn't you be? This is horrible. I mean, that's why there are news stories about this. I mean, a person's let go 20 years later after being on death row. They've lost a lot of their prime years of life. They're not going to have, families or kids, or it's hard to get jobs, etc. So this is terrible, terrible stuff. So if if you're really, really, really worried about this, what are you going to do? Well, you're going to make it so that coming up with the guilty verdict is harder to do. You put up a higher threshold, like you really, 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 really have to be sure before you can put somebody behind bars. But think what that's going to do. If you make it so that you never, 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 never want to do this, if you want to lower that down really, 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 really low, then what that's going to mean is you're going to get a lot more not guilty verdicts. But catching with all the correct decisions you'll be making, you'll also be letting go a lot of people that were guilty. And you'll cause beta to go up. So alpha is the probability of this one in the bottom left corner. Beta is the probability of this one in the top right corner. And if you lower your alpha, then your beta is going to kind of raise. Now, it's not like, a perfect relationship, but there is a relationship there, an inverse relationship. I like to say that alpha and beta are on a teeter-totter together, or a seesaw. I don't know what word you used. My family always used teeter-totter. So a lever, right, with a fulcrum. So if alpha goes down, beta is going to go up. And vice versa, by the way. If alpha goes up, beta is going to go down. There, and I tied those arrows together. So the red arrows go with if alpha goes down, beta goes up. Those are the red arrows. And then the green arrows will be if if beta goes down, then alpha goes up. Right? Another reason, by the way, that we can't make them 0, this is just straight up 0, is that if you did, then that would imply that you're 100% sure of what's going on. And of course, that's never the case. We never know. We just have certain confidence in what's going on based on evidence and data, but we don't know what's going on. There. So we're never 100% sure of our decisions, right? If you're going to set alpha or beta to 0, either one of them, that would imply that we were 100% sure, and that is not possible. Because that would imply that I am 100% confident, and 100% confidence is not possible. So we don't get to know reality, not in statistics. All right, so let's keep that teeter-totter idea in mind for this example down here. So we have Charlie performing a test at the 0.05 level of significance, and Felice will perform the same test at the 0.01 level of significance. Now, if the null hypothesis is true, who has the greater chance of making a type 1 error? Okay, well, remember that alpha, by definition, is the probability of making a type 1 error. So that means that Charlie will have the greater probability of a type 1 error because Charlie has the greater alpha level. All right, so now, who's going to have the greater probability of making a type 2 error? Well, that would be Felice, right? She has the lower alpha, so she's going to have the higher beta because they're on a teeter-totter together. I guess we don't really need this part up here. We need it down for letter B. So let me type that up real quickly. There. So Felice has a lower alpha, so that means her beta will be higher generally. This isn't rock solid, but this is the general rule of thumb. And therefore, she has a bigger chance of making a type 2 error. So if her lower type 1 error, higher type 2 error. Charlie has a higher type 1, so he would have a lower type 2 because they're on that seesaw together.